Hello guys, welcome to this example. We are going to solve by method of Laplace. Y prime prime plus 2y prime plus 4y equal to 4 exponential negative t. So this is a non-homogeneous case, and these are our initial conditions. Y of 0 equal to 2 and y prime of 0 equal to negative 1. So solution. So we begin as usual by taking the Laplace transform of both sides of the given differential equation. So this implies the Laplace transform of y prime prime plus 2y prime plus y is equal to the Laplace transform of 4 exponential negative t. Is that okay? Now, if we write the Laplace transform of the left hand side, gradually we'll write the Laplace transform of y prime prime. This is an s square, y of s, capital letter y of s, and minus s, we have y of 0, and minus y prime of 0. So this is the Laplace transform of y prime prime, okay, and plus 2, and the Laplace transform of y prime is s, y of s, then minus y of 0, okay. So this is the Laplace transform of y prime, and plus the Laplace transform of y is y of s. Is that okay? And it is equal to the Laplace transform of 4 exponential negative t. This is still 4 Laplace transform of exponential negative t. Is that okay? So let me group some terms here. I'll group all the terms that have y of s. So I can see an s square, I can see 2s, and I can see a coefficient of 1 here, all of them on y of s. Then I can see negative s, y of 0 on this particular place. I can see negative y prime of 0, and I can see from this place 2 times minus y of 0 is minus 2y of 0. Then this is equal to 4. Laplace transform of exponential negative t is 1 over s plus 1 from our tables. I hope we still remember. So we are going to now plug in our initial conditions on this for these particular expressions over here. The initial conditions are y of 0 is 2 and y prime of 0 is negative 1. Y of 0 is 2, y prime of 0 is negative 1. So we are going to have s squared plus 2s plus 1, y of s. Okay, then we now have minus y of 0 is 2, so s times 2 is 2s. Then you now have minus y prime of 0 is minus 1, minus times minus 1 is a plus 1. Then finally 2 times y of 0, which is 2 times 2, and that's on the negative sign, which is negative 4, is equal to, we have 4 over s plus 1, like this. So we have s squared plus 2s plus 1 y of s. Then you now have minus 2s, okay, minus, okay, plus 1 minus 4 is negative 3, okay, and this is equal to 4 over s plus 1. So I'll take these two terms to this other side. I'll have s squared plus 2s plus 1 y of s is equal to, I have 2s plus 3, then plus 4 over s plus 1, okay, like this. So we'll have s squared plus 2s plus 1, and y of s is equal to, so if we consider this one over here, adding up with this one, we'll have something like this. 2s plus 3 multiplied by s plus 1 and plus 4 over s plus 1, like this. Is that okay? So when you simplify, this is what you will get. Now we're going to make y of s alone, and you have 2s plus 3, into s plus 1 and plus 4 over I have s squared plus 2s plus 1. Then you now have what? S plus 1. Okay, this whole expression, right, for y of s, we normally call it transfer function. Okay, call it the transfer function. So when you start dealing with control theory, introduction to control theory, you're going to be working with a lot of transfer functions. But just know for now that this is our transfer function for this system. So the expression y of s is called the transfer function. Now look at this factor in the denominator, this quadratic factor. You agree with me that it can be factorized. In fact, s squared plus 2s plus 1 is s plus 1 all squared. Okay, if you remember, so y of s is actually 2s plus 3, then s plus 1 plus 4 over, this is s plus 1 all squared, right? Multiplied by s plus 1, and this becomes 2s plus 3, then you now have s plus 1 and plus 4 all over s plus 1 cube. Now I am going to distribute this denominator to the terms in the numerator, and I'll have 2s plus 3 s plus 1 divided by s plus 1 all cube, then plus 4 over s plus 1 all cube. Okay, I hope you understood the distribution of the denominator to the terms in the numerator. I distributed this numerator here to this term and this term, so it is mathematically correct, so that s plus 1 cancels out 1 s plus 1 from here. So we're now left with y of s is equal to 2s plus 3 over s plus 1 all squared, like this, and plus 4 over s plus 1 all cube. Okay, at this point we can take the Laplace transform, Laplace inverse of both sides to obtain our y of t. So taking the inverse Laplace transform of both sides, you have Laplace inverse of y of s is equal to Laplace inverse of 2s plus 3 over s plus 1 squared plus 4 over s plus 1 all cube. Is that okay? So the Laplace inverse of y of s is your y, which is your y of t. Okay, remember y of t and y of s, capital letter y of s, form a Laplace transform pair. Okay, the y of t and capital letter y of s form a Laplace transform pair. That is why when we took the Laplace transform of y over here, this y is still y of t, we got y of s. Okay, so take note of that. So back to this point, the Laplace inverse of y of s is your y of t. Then we now have the Laplace inverse of 2s plus 3 over s plus 1 all squared plus the Laplace inverse of 4 over s plus 1 all cube. Okay, so I am going to show you some new things that I probably did not say in the first video, but I just want you to follow me as much as you can. Okay, so first of all, let's start with this particular term over here. So consider 2s plus 3 over s plus 1 all squared. This is still the same thing as 2s plus 3 over s plus 1 and s plus 1. Linear factors that are repeated gives me a over s plus 1 and plus b over s plus 1 all squared. Okay, so when you're expressing it in terms of partial fractions, so 2s plus 3, okay, when you multiply this right hand side by this whole denominator, you're going to get a into s plus 1 and plus b. Of course, when you open the bracket, 2s plus 3 is equal to as then plus a plus b. Okay, when you compare coefficients, comparing coefficients, a is attached to the s term on the right hand side and 2 is attached to the s term. So a is equal to 2. So the constant term on the left hand side is 3, while the constant term on the right hand side is a plus b. So 3 is equal to a plus b. And for a equal to 2, a plus b, the implication is that our b is equal to 1. Is that okay? When you solve it for a equal to 2, so b is equal to 1. So we have resolved this term in partial fractions. So 2s plus 3 over s plus 1 all squared is still the same thing as you having 2 over s plus 1 and plus 1 over s plus 1 all squared. Is that okay? So we are now going to have finally our expression for y of t as this: Laplace inverse of, instead of 2 over s plus 3 over s plus 1 squared like we had here, we're going to use the partial fraction, which is 2 over s plus 1 and plus 1 over s plus 1 all squared like this. And finally we will now have plus the Laplace inverse of 4 over s plus 1 all squared, all cubed rather, like this here. So I'll still distribute the Laplace inverse operator. So the Laplace inverse of 2 over s plus 1 plus the Laplace inverse of 1 over s plus 1 squared plus the Laplace inverse of 4 over s plus 1 cubed. Okay, you can still do some manipulations with the constant term over here. So doing some manipulations, we'll have our y of t is equal to 2 Laplace inverse of, just like integration, 1 over s plus 1. Then this one is already intact. Laplace inverse of 1 over s plus 1 all squared. And this is 4 Laplace inverse of 1 over s plus 1 cube. Okay, so I'm going to copy out this expression over here, and we're going to use it on a new section of our page. Okay, so we're going to use it here. So this is where we stopped. Now you want to find the inverse Laplace transform of these things. You're seeing these particular forms. Okay, this form is very well recognizable. In fact, y of t is going to be, for this place I'll have 2. Okay, when you take the Laplace inverse of this term 1 over s plus 1, you get exponential negative t, okay, from the table, or exponential minus 1t. Okay, so going over to this term and to this term, so how do we resolve it? So this is where we have some little problem. But before we find out the Laplace inverse for this term and for this term, I just want to remind you of something. Okay, a new theorem. So that theorem is called first shift theorem. So the first shift theorem in Laplace transform teaches us that when we take the Laplace transform of exponential at multiplied by a function f of t, okay, when you multiply an exponential by a function and when you take the Laplace transform, you're going to get an f of s minus a. Okay, so f of s is actually the Laplace transform of f of t. So basically what you're just trying to say is that if you know the Laplace transform for f of t, okay, which is going to be f of s, and anytime that you're having an exponential at multiply your f of t before you take the Laplace transform, just carry out a shift. Okay, this particular shift is called right shift. Okay, first shift theorem or right shift. So a right shift is when we shift the a in the brackets, okay, when we shift the the frequency parameter a units to the right, and that is usually associated by a minus sign. So instead of you to whenever I'm giving a Laplace transform of exponential at times f of t, okay, since this is an exponential term, I just need to know what is the Laplace transform of exponential of f of t. Sorry, if I know the Laplace transform of f of t, okay, which is going to be f of s, instead of me to write f of s, then my answer will now be f of s minus a. Is that okay? F of s minus a. So for instance, assuming I want to take the Laplace transform of exponential 2t times, let me say t square, for instance. You want to take the Laplace transform of exponential 2t times t square. Remember, for polynomials, the Laplace transform for polynomials of t raised to the power of n is n factorial over s raised to the power of n plus 1. So for t square, the Laplace transform for t square is going to be 2 factorial over s raised to the power of 2 plus 1, which is 2 over s raised to the power of 3. Okay, this is the Laplace transform for what? T square. But because of this particular parameter over here, this particular 2 over here, the Laplace transform of exponential 2t times t square is going to take the shape of the Laplace transform of what? It's going to take the shape of the Laplace transform for t square, but this time around you're going to carry out a shift on s. So instead of you to have s, you're going to have s minus what? 2 over here, or cube. So this is how to find the Laplace transform of shifts, right? Shift theorem. So that's basically what this thing means. Is that okay? Similarly, if I have something like this, Laplace transform of exponential minus 2t, then let me say t itself, and I want to find the Laplace transform of this particular value over here. You now agree with me that the Laplace transform of t, just solve the Laplace transform of t somewhere, is 1 factorial over s raised to the power of 1 plus 1 according to this formula. The Laplace transform of t is 1 over s squared. So because of this particular term over here, the Laplace transform will be, I'll now carry out a shift on s by subtracting minus 2. So it will be s minus 2 all squared. So this will now give me 1 over s plus 2 all squared. Okay, so this is the Laplace transform of exponential 2t and t. Remember, it is actually taking the shape of t itself. So all you just need to do is to carry out a shift by subtracting, reducing s by whatever the value is here. Okay, if it is negative, then it will eventually turn to plus. And if it is positive here, to be minus. Is that okay? So just try to meditate on this theorem. Now, using these particular two things that we have established here, I want us to find the inverse Laplace of this and the inverse Laplace of this. You can already see that this one is taking the shape of 1 over something cube. Okay, and 1 over something cube is usually associated with what? The Laplace transform of our t square. So the only thing that is missing here is a 2 here. So I can add a 2 here, okay, and I can divide by a 2 here. Do you understand? I can add a 2 here and I can divide by a 2 here, so that the Laplace transform of t square will be complete in this form. So the only difference is that I can see there is a shift in the s parameter, and this s, okay, plus 1 is still the same thing as s minus 1 if you look very carefully. So this particular one is already taking the shape of the Laplace transform of t. If you look at it very well, this particular first term is taking the shape of the Laplace transform of t, and the Laplace transform of t is what? 1 over s squared. It's just that I have 1 over something squared, and the something is s minus 1 all squared. Okay, so this term over here is actually the term of interest, which is a minus 1. Now, if you take the Laplace inverse of this term, we're going to get plus, there is a shift, and that shift is the contribution from exponential minus t. Okay, then the shape this one is taking is t itself. Is that okay? Then plus 4 divided by 2 is 2. Okay, then the Laplace inverse of this particular one is actually taking the shape of t square, of course, the Laplace transform of t square, but you need to acknowledge the shift, and the shift is the contribution from exponential minus t. Okay, exponential minus 1t, okay, just like we established here. So this is the formula for finding, or this is the concept of solving this kind of Laplace inverse. So our y of t at the end of the day is exponential negative t into 2 plus t and plus t squared, 2t squared, like this. Is that okay? So yeah, I'll leave it for you to meditate, and I'll leave it for you to ask me questions. Okay, so this shift theory might be a little tough, but I wish you can spend time to ponder and meditate on it so that you can grab the concepts very well. So this is about the Laplace transform for ordinary differential equations. And this example that we solved, this is the concept. This is where we arrived at, and I hope you could try to reproduce this problem on your own. Maybe it could come out in an exam. They could just give you the transfer function and ask you to obtain y of t. So you have to take the Laplace inverse, carry out some partial fractions, and you should be able to remember this shift theorem, very important. So let me just generalize the shift theorem. The Laplace transform of exponential minus at times f of t, okay, is going to give you an f of s plus a, okay, because here is minus, okay, it will be plus, but if here is plus, it will be minus in this case. So all you just need to know is to know the form of f of t. What is the shape that the Laplace transform of f of t takes? So if you know the shape, you can now apply the shift, for instance. Okay, apply the shift, for instance. So let me just give something to round it up. Assuming I want to find the Laplace transform of exponential minus 2t then times sine 3t. Is that okay? I don't need to struggle. I just need to know what shape the Laplace transform of sine 3t takes. So the Laplace transform of sine 3t actually takes this shape. It takes, according to the formula, it will be 3 all over s squared plus 3 squared, which is 3 over s squared plus 9. Okay, so what I just need to do is to shift s by minus 2 units to the right. So shifting s minus 2 units to the right will mean the Laplace transform of expression minus 2t then sine 3t. Okay, that is now going to give me a 3 like this, divided by, I'll shift s minus 2 units, so that's s minus minus 2, which is an s plus 2, then all squared plus 9. So this is it. Okay, so I hope you understood this. So I'll leave an assignment for you and post your answers in the comment section. What is the Laplace transform of exponential minus 2t and cos 7t? So leave your answers on the comment section so that I'll know you understand what I have just taught you now. And this example, please try as much as possible to meditate on it and solve it. I wish you all the best. Thank you for watching this video. Like, subscribe, hit the notification button, and you could always reach out to me if maybe there is a concept I explained and you didn't understand, and I'll be happy to show you the way as to how to go about it. So thank you very much for watching, and I hope to see you next time. Good luck in all your exams and in all your papers, your studies. Bye.